near pub called Casa Temple. It's in Palermo near the coast. The address is Costa Rica 4677. This is completely optional and it's more for the socializing among us. So if you want to come tomorrow after the last talk,
What are you thinking about?
What?
What are you thinking about? I'm sorry, I arrived.
Okay. Tomorrow after the last talk, we are going to a brewery that's called Casa Temple. It's near the coast.
Beer shop.
Yeah, beer bar. You are invited if you want to come. Yes, Costa Rica. Okay.
What's the name of the bar?
Casa Temple. It's written there. Okay, if you want to come, you're invited. Let's start with the last session of today.
Okay, thank you. We can continue. Okay, lecture 4 on the CMB. I would like to start by reminding what we did in the second half of the last lecture. We have realized that the key quantity that we want to predict and compare to the data is the temperature spectrum CL, which is an integral of the Fourier modes of the primordial spectrum times the square of the photon transfer functions for the multiple L, the wave number K, computed today. And because this theta L obeys to a super complicated Boltzmann hierarchy, we decided to evaluate it using the clever line of sight integral, in which theta L is given by a sum over time of 3 terms corresponding to 3 different physical effects. There is the effect of the intrinsic anisotropies on the last scattering surface corrected by the Sachs-Wolf term. There is the effect of the Doppler velocity on the last scattering surface. And there is the effect of the integrated Sachs-Wolf effect integrated along the line of sight. And so we realize that to get our CLs, we only need to know the behavior of the function theta 0, the monopole of the photons, at the time of decoupling, theta b, the velocity of the photon at the time of the decoupling, and there is a comma k that I have still not corrected, I will, and the metric fluctuations need to be known at any time after decoupling. So then our goal was to understand the evolution of only this function. But again, this function can be understood only if we have a simple equation of motion. And this is where we use this tight coupling approximation, pretending that photons and baryons remain tightly coupled until recombination. And then we had the second order differential equation. We explained the role of the different terms. And knowing this role, we had all these long discussion for the evolution of the quantities for one mode. And then we had the summary for all the modes taken together for the metric, and then for the temperature of the photons. And at the end of this discussion, we knew we could understand what was the shape of the transfer function for these relevant perturbations at the time of recombination and as a function of wave number k. And we said, okay, if we know our function at recombination for the wave number k, since there is a one-to-one correspondence between values of k and of wavelengths on the last scattering surface, the angles under which we see them and the multiple L to which they contribute, this can be used to give us a sketch of the CLs. And this is when we did this plot, which was one of the last plots, in which we try to go from the transfer functions to the CLs. And first, yesterday we only looked at the role of the first of the 3 contributions to the CL, which is the contribution of the intrinsic temperature anisotropy corrected by the gravitational Doppler shift given by this light blue function. We said, okay, the transfer functions are always squared in the integrand of the CLs. So we squared it, and we got this pattern with a plateau, which comes from the fact that on large scales, there was no evolution. These modes were super Hubble outside the Hubble radius. So this transfer function is flat because everything was frozen outside the horizon. And then we have the series of peaks corresponding to the fact that there was a propagation of acoustic waves in the early universe. And at the time of decoupling, we catch the modes when they had half a period, 1 period and a half of oscillation, etc. We commented on the details of this plot, on the asymmetry between even and odd peaks coming from the baryon effect, and the fact that we have an exponential damping here coming from the diffusion damping effect, also called Silk damping effect. And then from the square to the CLs, it's very intuitive. The shape is the same. What we did from here to here is that we use the integral over k of the square of this transfer function multiplied by the primordial spectrum. And I told you that it makes sense to plot here LL plus 1 CL, because if this transfer function was flat, so if there was no physical evolution whatsoever of the modes, you can use the formula for the CL to prove analytically that CL would be proportional to 1 over LL plus 1. You get this using a famous formula of integration over spherical Bessel function. And so LL plus 1 CL would be constant. And indeed, for small values of L, which correspond to small values of K, and thus to very large scales, which are still super Hubble at decoupling, we do see a horizontal shape, which is called the Sachs-Wolf plateau. And this shape just reflects the initial condition, the primordial spectrum, and nothing else. But on smaller scales, the initial scale invariant spectrum has been modulated by the acoustic oscillations, and thus the quantity LL plus 1 CL is also modulated. And so we commented on the fact that the patterns of the CL look very much like the pattern of the square of the transfer function, but in a smoothed version, meaning that there are no zeros here, and the peaks are not so high and wider. And we say this is an effect of smoothing, the smoothing corresponding to the thickness of the last scattering surface, which enters mathematically in the width of the visibility function and in the width of the peaks in the Bessel functions. And this is exactly where we stop. If you already have some questions because you forgot something, you can ask me now. Otherwise, I will go into some new stuff. Good. So, now this is not the full final CL. It is a CL, the temperature power spectrum that we would get if in our line of sight integral we would only consider the intrinsic anisotropies. But we have still neglected the Doppler effect and the integrated Sachs-Wolf effect. Let's try to go beyond. But before, I would like to give you another summary of the situation, because what is very confusing when you study CMB physics, and what takes a lot of effort to understand, is that sometimes we describe things in real space and sometimes we describe things in Fourier space. The analysis that we are carrying is always in Fourier space, and it's good to think about what is really happening in real space. And it is a goal of this slide. This slide is not to be taken too seriously. It's just to guide your intuition. Now forget Fourier space and try to think what it means that there are acoustic oscillations in real space. So I have here the axis of time, and I assume that we are the observer. We are here. And we look at the last scattering surface. Before last scattering, things happened in the tightly coupled photon baryon fluid. And in particular, in this photon baryon fluid, they were overdensities created by inflation. Suppose that in this direction, I had at initial time an overdensity. This overdensity will propagate in the form of acoustic waves. If the overdensity would be spherical, which is a bit naive, the acoustic wave would also have spherical wavefronts. But in this cut, where I have one dimension of space and one dimension of time, the wavefront corresponding to the propagation of the acoustic wave from this point corresponds to this trajectory. So the acoustic wave would travel by a distance, and this distance is a distance over which sound wave can travel. So it's an integral over time of the sound speed in the medium. This integral defines what is called the sound horizon, ds. If we would compute the sound horizon in comoving coordinates, in comoving scales, we would take the speed of sound and we would just integrate it between the early universe and an arbitrary time eta over conformal time. And this gives a comoving sound horizon. To get the physical sound horizon, we need, as usual, to multiply by the scale factor at this time. And this gives a very well-known definition of the physical sound horizon at time eta. So the distance here over which the wave travels is a sound horizon, and at the time of decoupling, we get here the sound horizon computed at decoupling. And we will receive photons from these points. So this photon, if there was an overdensity here, will be hot because they come from the propagation of the hotspot that was created here by inflation. But in this direction, there should be also a hotspot because the wave have propagated in all directions. So we expect that these 2 points of the last scattering surface should be statistically correlated because they both carry information about this unique overdensity created in the early universe by inflation. And this is a mechanism that tells us that there should be statistical correlation on the last scattering surface between any 2 points separated by 2 times the sound horizon. If there is a correlation, when we take the 2-point correlation function, there will be a feature, there will be a peak. And this peak is the first peak in the CLs. And we have other peaks in the CLs, which are regularly spaced, just because we have the harmonics. So the spectrum in multiple space is like a spectrum in Fourier space. We have the harmonics of the first peak. And if we elaborate a little bit on this, we have a way to predict analytically in a given cosmology the multiple at which the first peak should be observed. In my plot, I had here an overdensity. This overdensity had propagated, so I have here a hotspot and here a hotspot. So this pattern contributes to a Fourier mode which has a wavelength equal to 2 times ds with a maximum here, a minimum here, and a maximum here. It means that I see, for this mode, I see the maximum and the minimum separated by a distance ds, and I see this distance ds under an angle theta s, fulfilling the relation angle equal distance divided by diameter distance, the diameter distance of cosmology, the one that Ruggiero defined. So theta s, the angle under which I see the separation between a maximum and a minimum, should be the ratio of the sound horizon at decoupling divided by the angular diameter to decoupling. But when I see patterns where maxima and minima are separated by an angle theta, it means that in multiple space they contribute to the multiple pi over L. To the multiple L such that theta is equal to pi over L. And so this relation, pi over L equal ds over dA, gives me a prediction for the position of the first peak. And it works very well. If you have a cosmological model, you only want to know where the peak is, but you are not interested in the details. You only integrate the equations of background cosmology. they will give you the sound horizon, they will give you the angular diameter distance for given cosmological parameters. You take the ratio, you invert it, you divide by pi, and you get the peak L, the value of the peak L. And the other peaks are regularly spaced and can be inferred from the first L. So this is the intuition that you can have in real space. That's very useful, but when you want to be precise, when you want to understand the details of the spectrum, then you have to go again to Fourier space. And this is what we are doing in most of the lecture. Okay, questions on this real space? Yes. We are seeing the sum of all the waves imprinted on the last scattering surface. All the waves at all wavelengths, but we catch them on the last scattering surface. This is why we had to study at some point the way in which a Fourier mode observed on a sphere projects to multiple space. No. We have many peaks because we have a single correlation length. So if we would compute the correlation function as a function of angle, we would have a unique peak. But then, you know, when you have a two-point correlation function in real space with one peak, in Fourier space, it has many peaks, which are the harmonics. Because if I have a maximum here and a minimum here, it could be because I have half a wavelength between the two. But it could be also because I have a much smaller wavelength with maximum, minimum, maximum, minimum. This is the first harmonic, and so on and so forth. Yeah. Very good. Okay. What is left? Well, we don't have still our full CLs. We have the contribution to the CLs from intrinsic anisotropies and Sachs-Wolf correction, but we still don't have the Doppler effect, and we still don't have the integrated Sachs-Wolf effect. Yes? What is? Theta S is the angle under which we see the sound horizon.
What is value in degrees?
Ah, yes, 1 degree. 1 degree, yeah. Very good. Very close to 1 degree.
I approximate this to the Hubble scale at the coupling. Do I make a big mistake?
No, that's a good point. Because if you would like to compute the Hubble scale at, okay, the reasoning is the following. So Ricardo says, okay, the sound horizon is probably of the same order of magnitude as the Hubble scale at the horizon. Yes, why? Because here I have the sound speed, which is approximately 1/√3. If I take instead the sound or the speed of light, I make a small mistake by a √3. And this expression becomes the causal horizon instead of the sound horizon. And you can always show that in a universe in decelerated expansion, the causal horizon has the same order of magnitude as the Hubble scale. So indeed, the sound horizon has the same order of magnitude as the Hubble scale at a given time. And so this scale under which we see the oscillation is of the same order of magnitude as the Hubble scale on the last scattering surface. Very good. Okay? Yes?
If we're seeing different waves,
Yes, we see a superposition of all possible waves because they have all been excited by inflation and they have all propagated and they have all created correlations. Yeah.
you have different EF. Why you see one?
No, because all the fluctuations travel at the same sound speed. So the correlation length is always the same. Yeah. Okay. Okay, so we are going to try to add the missing effects, and we try first to add the integrated Sachs-Wolf effect. The integrated Sachs-Wolf effect was an integral along the line of sight of phi prime plus psi prime. So this effect is non-negligible, we said, when there is an evolution of the metric fluctuation as a function of time. And we say that the integrated Sachs-Wolf effect is by definition after recombination when along a vertical line, I see a gradient of color on my plot. And this happens only in few places. In most places, phi is either 0 or non-zero, but constant during matter domination. So in most of the plot, there is no contribution to the integrated Sachs-Wolfe effect, except it on scales crossing the Hubble radius just after recombination, because we are close to radiation domination, and the decay of phi is not completed. So we have a region here. This we already mentioned, I'm reminding you. And we also have a decay of the gravitational potential during lambda domination, which means in this small region. So these two regions will contribute to the integrated Sachs-Wolfe effect. But you see there are two distinct effects called the early and late integrated Sachs-Wolfe. And so these effects will project to different multiples at the end. And indeed, this is what we observe. In particular, we expect that the early integrated Sachs-Wolfe has to do with large k, so small wavelengths, seen far from us under a small angle, and so it should contribute to a relatively large L. The late integrated Sachs-Wolfe has to do with small k, so very large wavelengths, very close to us, so we should see them under a very large angle, and that should contribute to a small multiple L at the end. And it's exactly the case. The early integrated Sachs-Wolfe effect is a small contribution in red with a peak corresponding to the raise towards the first acoustic peak. While the late integrated Sachs-Wolfe effect peaks actually at the smallest multiple that we can observe, which is a quadrupole. We don't take the dipole into account because it's dominated by the bulk velocity of the observer. So the late integrated Sachs-Wolfe effect, you see, these effects are small, they are small correction. The late integrated Sachs-Wolfe effect is at small L. The early integrated Sachs-Wolfe effect is at intermediate values of L. So this is another contribution. Which one are we still missing? We are missing the contribution of the Doppler term. But we can guess what the contribution of the Doppler term is because it comes from the pattern for the transfer function of the bulk velocity of the baryons. And we say that this pattern is intuitive. It corresponds to the derivative of theta 0. And like position and velocity in a harmonic oscillator, it is out of phase with the oscillations of theta 0. So now I can take the square of the green curve, theta b, and compute what is the contribution of the Doppler effect to my CL spectrum. And I find that there is no contribution on small scales because on small scales there is no bulk velocity effect. But then there are peaks which are out of phase with the peaks of the acoustic oscillation. And that's interesting because the Doppler effect tends to fill the deficits created by the intrinsic temperature. Here, for instance, we had a dip. This dip will disappear because it corresponds to a maximum of the Doppler effect. And so in principle, these are all the contributions. And naively, I should take the sum of these curves to get my final CLs. This is almost true, but visually you will maybe realize that it's not completely true. The black curve, which is a total, looks reasonably like the sum of the other curves. Okay, with a plateau, no dip because of Doppler, and then we raise to the first peak, and we have the series of peaks. But it's not quite the sum. Okay, if you sum these curves, you don't arrive as high as to this first peak. And why? It's because we should not sum the square of the transfer function, but there are cross-correlation terms that we have to take into account. In the integrand of the CLs, everything is squared. So like a plus b squared is a squared plus 2ab plus b squared. We will have cross-correlation term corresponding to the cross-correlation between, for instance, intrinsic temperature and Doppler, or intrinsic temperature and early integrated Sachs-Wolfe. And I've not shown this cross-correlation, but I could. And then we would get a few other curves. And the total of all the curves, including the cross-correlation, would really be exactly the same as the black curve. So now we have a very good qualitative understanding of the shape of the final CLs. And you see that it's really not a trivial quantity, neither to compute nor to understand, because it depends on a sum of many subtle effects. But at the end, we have our Sachs-Wolf plateau, our acoustic oscillations, our asymmetry between the first peaks created by the baryon shift of the 0 point of oscillations, and our exponential damping of the high L peaks created by diffusion damping. So all the physical ingredients that we studied before. And now we can do a nice summary of what should be the effects of the parameters of the lambda CDM model on the CLs. I really like discussing this usually because it's not obvious for many people, even people who work on the CMB, that all parameters have at the end a relatively simple effect, and the most important is to prove that in the parameters of lambda CDM have very different effects from each other, and that these effects are not degenerate. So I will give this discussion in short version because I love this topic, so I can also give it in a long version, but I will not do it. I will try not to spend more than 20 minutes on this. Just to recap, what are the effects of the different parameters on the shape of the CLs? And so first, we should choose our basis of cosmological parameters. We have the choice because we know that the lambda CDM model, the minimal one, has 6 parameters, but we have different ways to choose a basis of parameters. So first, really, we stick to the minimal model in which there is no spatial curvature. The cosmological constant is truly constant. Dark matter is a boring, decoupled, stable particle and completely cold. The neutrino mass will be either here neglected or assumed to be fixed to their minimal value. Tomorrow we will talk briefly about the effect of neutrino masses. We will assume no other exotic relics or dark radiation beyond the usual 3 families of neutrinos. And we will assume a simple power law primordial spectrum from minimal models of inflation. So all the simplest assumptions. And then we are left with 6 parameters. In the course of Ruggiero, this would have been 5 because in large-scale structure, the optical depth of rayonization plays absolutely no role. But in CMB physics, it does play a role. It's a parametrization of the integrated effect of the scattering of photons during rayonization. So we have a choice for our basis. For instance, for each species, we can choose a big omega or a small omega. And in the jargon of cosmologists, you probably know that small omegas are a notation for big omega times h squared. And if you don't know why the hell are we interested in this combination? It's because a big omega is a relative density parameter. It parameterizes the density of a species relative to the critical density. But the critical density is proportional by definition to the Hubble parameter squared. So if I multiply my omega by the reduced parameter small h squared, I get a new dimensionless parameter, which parameterizes not the relative density, but the absolute density. And I could, in fact, multiply by a constant and convert my small omega in a true density in gram per centimeter cube. There is a coefficient that happens to be 10 to the 26 gram per centimeter cube. And I choose here to parameterize baryons and total non-relativistic matter with a small omega, because it's really the absolute density of baryons and matter which plays a role in the shape of the CLs. So I have small omega b and small omega m, where small omega m is omega b plus omega cold dark matter. It's all non-relativistic matter. For the cosmological constant, I am not interested in the absolute value of the cosmological constant. I just need a parameter that tells me when the transition from matter to lambda domination occurs. And this big omega lambda is perfect for this. It gives us a redshift of equality between matter and lambda. Then we have our optical depth of rayonization and the amplitude and the spectral index of the primordial spectrum from inflation. So we have these 6 free parameters in the minimal model. Yes? They are all today values. Yes, absolutely. That's a very good point. We do care about radiation, but once you have measured the temperature of the CMB, 2.7255 kelvins, you know the density of photons. It's not a free parameter anymore. And once you have assumed the standard effective neutrino number, you know also the density of neutrinos relative to photons. And omega r is no longer a parameter. Otherwise, you are perfectly right, we should have a small omega r. But in the minimal standard model, this is known up to 4 digits. That's why, yes. Yeah.
Makes sense when we assume that it's 0 and later we have omega matter around the lambda. It's consistent with that assumption. What if we assume that's not 0 and we do everything?
That what is non-zero? Omega k? Omega k. Tomorrow we will relax omega k equals 0. I will show you the impact on the CLs. Okay? It's just that I don't want to confuse you by putting all the effects at the same time. So first, today we fix omega k to 0, and tomorrow we will see what happens when omega k is non-zero. Okay, so this is our basis of parameters, and we will play a small game. In all the next slides, there will always be a reference spectrum in black, which corresponds to the CLs for typical values of the parameters, very close to the best fit of current data. And then we consider the parameters one by one, and we increase them. And when we increase them, the plots become redder and redder. And for some effects, for some parameters, the effect is totally trivial. And the most trivial is the effect of the amplitude parameter AS. Why? Because the CLs that we compute have a PR here. And PR is proportional to AS. So the whole CMB spectrum is proportional to the amplitude parameter. If I increase AS, I rescale the whole shape. Completely trivial. Second effect, also very simple. What happens when I fluctuate NS? When I fluctuate NS, it means that I change the power law in the primordial spectrum. And so I tilt this whole ingredient, giving more or less power to small k compared to large k. But at the end, we have seen that there is almost a one-to-one correspondence between a value of k and a value of L because of some convolution with very peaked functions. So if I tilt the integrand as a function of k, I should tilt the whole spectrum as a function of L. And then this tilting means that when the small scales are suppressed, the large scales increase. And there should be a scale which is left invariant. The scale which is left invariant should depend on the arbitrary pivot scale that we define in our primordial spectrum. That's just an arbitrary choice. This pivot scale in K space will give us a pivot scale in L space at which a spectrum is invariant, and we see this shape here. And now you will tell me, yeah, on this plot, I see that when you increase NS, this scale is left invariant. Smaller L's are suppressed, larger L's increase, but they don't seem to increase very much. No, but this is because at the end, the spectrum is always multiplied by an exponential damping tail. This is why you don't see as much increase here as you see a decrease here. But you are tilting your spectrum. If NS increases, you have less power in the Sachs-Wolf plateau and more power in the secondary peak. So the effect of NS is among the simplest ones. The effect of omega b starts to be much more interesting. We see that when we increase omega b, there are lots of things taking place. First, the scale of the peaks. It changes. All our peaks move to the right. Larger L, smaller angular scales. And if we would draw the exponential damping envelope, we see that the envelope of the black curve is not the same as the envelope of the red curve. So the scale of the damping envelope is also shifted towards smaller angles. And then even more striking, if we look at the amplitude of the peaks, we see that the first one increases considerably, the second one decreases, and the third one decreases a little bit again. And all these ones decrease for a reason that we will give. Okay, so can we interpret this? Yeah, we can interpret everything as a combination of the physical effect that we have studied yesterday. So here are the three effects that are at play. Concerning the scale of the peak, we said pi over L is ds over dA, sound horizon over angular diameter distance. The sound horizon is an integral that contains the sound speed. The sound speed, you can check the formula of yesterday, is the square root of 1 divided by 3, 1 plus r, where r is a baryon to photon ratio, rho b over rho gamma, with a factor 3/4 in front. If I have more baryons, it means that at the time of decoupling, r is bigger, so the sound speed is smaller. So I change the value of the sound horizon because Ts appears in the integral. And so I shift the peaks. And so the shift of the peak comes from a change in the sound horizon at decoupling, triggered by a different value of the baryon density in the universe. This envelope here has a scale given by the angle under which we see the diffusion scale. The diffusion scale is a guilty factor for this exponential damping. Remember, it gives you the scale on which all fluctuations are erased by diffusion. The diffusion scale, lambda d, was defined in the lecture on Monday. We see it under a given angle, and the reasoning to get this angle is the same as for the sound horizon. The ratio of lambda d over the angular diameter distance corresponds to an angle, and this angle is a pi over L. So this formula gives a typical L corresponding to the scale of the damping. In lambda d, there was a Thomson scattering rate. The Thomson scattering rate depends on the number density of electrons in the universe, which is equal to the number density of baryons due to electric neutrality. And so lambda d changes when you change the density omega b. And this is why the scale of the damping envelope is also shifting. And the most interesting effect, why is it the most interesting? Because it's very unique, cannot be mimicked by other parameters, is the fact that while increasing the first peak, we decrease the second one. And this we have explained well enough, I think, yesterday. But let me repeat. Our acoustic oscillation have a 0 point of oscillation set by -1 plus r psi. It was a dotted line in the plots yesterday. And it comes from the fact that the mass of the baryon breaks the symmetry between the compression and the rarefaction in the propagation of acoustic waves. If we have more baryons, we enhanced R, the value of R, because R is baryon to photon density ratio. So we exaggerate this asymmetry, and we exaggerate the asymmetry between odd and even peaks. And this is why the first one goes up, while the second one goes down. And with these three effects, you can understand the impact of a variation on omega b on the CMB.
And the position of the first peak you fix, I mean, not affected by change omega b, because you offset with some other parameter?
No, the position of the first peak is not fixed. What we fix in these plots is all parameters but one. We are fixing all parameters but one. And the fact that omega b varies then has an impact on the sound horizon and thus on this scale. This is why the peak is shifted.
Just me, I don't see visually, but it does change the position of the
It does change. It's easier to see on the other peaks, but they all change by the same amount. So from here to here, there is a shift to the right. Okay, that was for omega b. Then for omega m, we can play a similar game. This is the effect. It's different because now the first two peaks go down. They are still at a different scales. Now the scale of the peaks moves to the left when we increase omega m. And the diffusion envelope is also shifted. So again, this is a combination of three effects. the first effect is again coming from the calculation of the angular scale of the peaks. Why is it relevant to change omega m? The parameter small omega m gives the density of matter in a cosmological model. The density of radiation is fixed exactly for the reason that we said when I answered your question. So when we change omega m, we change in fact the ratio of matter to radiation in the universe. We change the redshift of equality between matter and radiation. But this is relevant because in the sound horizon, you have an integral over all times until recombination. If I change my expansion history before recombination, I change the integrand in ds. And thus I change the sound horizon at recombination. This is why the peaks are moving. And we have exactly the same effect here. When we change omega m, we also change the expansion rate before recombination. The integral in lambda d changes, and we change this value. For omega m, it's even a bit more complicated than for omega b. We actually change also the denominator, because if you try to compute the angular diameter distance to recombination in this basis, you will find that it also depends on omega m. But also, this is a detail. So, a change of omega m changes the angular scale of the peaks and the angular scale of the damping envelope. But it does also something else which is unique and which is responsible for the decrease of the first two peaks. We have changed the redshift of equality. But the redshift of we have not changed the redshift of recombination. So in the history of the universe, equality takes place at a different redshift, but recombination always at the same redshift. So we change the amount of time and expansion between equality and recombination. In some cosmological models, and depending on the value of omega m, you can have a long stage between equality and recombination or a very short stage. But recombination will always take place after equality for all reasonable parameter values. This is important because we say that during matter domination, the metric fluctuation remains stable, while during radiation domination, they decay when crossing the Hubble radius, which leads to a gravitational boost effect, increasing the amplitude of the oscillations. So I know this is a lot of information. Actually, I'm not expecting that you will remember this. What I want to show you is that by assimilating all the effects that we have studied yesterday and by being patient, it's possible to reconstruct all these non-trivial parameter effects. So when I change omega m, I change the amount of time between equality and decoupling. It means that I change which scales are affected by the gravitational boost and which are not. And indeed, with a bigger omega m, these scales are less affected by the gravity boost. This is why the amplitude is smaller. And moreover, I also change in this case the early integrated Sachs-Wolfe effect, because if equality takes place just before decoupling, there is a very strong early integrated Sachs-Wolfe effect, since the metric fluctuations are not yet stabilized. If equality takes place a long time before recombination, the metric fluctuation will be totally stabilized at recombination. We will have no partial derivative of phi m psi and no early integrated Sachs-Wolfe effect. And this is also responsible for the variation of the amplitude in this range. Once you realize that there is a way to explain these effects, you become very curious and maybe more motivated for studying again all what we have said in more details. So what I want to show you is that it's not impossible to actually understand why these curves depend in a very precise way on all the cosmological parameters. The Boltzmann code are not a black box in which you put your parameters, you see some effect, and you don't even try to understand what's going on. You can try to understand what's going on. It's not so difficult. Just requires work and practice. Omega lambda is much easier. What do we see? We see just shift of the peaks, shift of the damping envelope and change in the tilt of the Sachs-Wolf plateau. That's very easy to understand. The angular scale of the peaks and of the damping envelope that I forgot to put, I will add it, change, because if I change omega lambda, I change the expansion rates now in the recent universe, right? Not in the early one, in the recent one. I change the time at which we transition from matter domination to lambda domination. And then I will not change the sound horizon at decoupling because it's given by an integral over all times until decoupling. But I change the angular diameter distance to decoupling, which is given by an integral from decoupling until today. So I change dA. If I change dA, I shift this ratio, I shift the value of L at which I see my peaks. If you remember, there is a similar formula for the damping scale. And in this formula, same story. The numerator will not change here, but the denominator will change because it's again the same angular diameter distance. And this is why actually the change in the scale of the peak and in the scale of the damping envelope is exactly the same in this case, because it comes from the variation of the same function, the angular diameter distance, to recombination or decoupling. And now this is obviously coming from the fact that when I change omega lambda, I change the duration of lambda domination, and so I have more or less of this late integrated Sachs-Wolf effect. And if I have a lot of late integrated Sachs-Wolf effect, given what we saw before, I have an extra contribution to small l's, and I shift my Sachs-Wolf plateau. We have seen all the effects but one. We are missing just the effect of the optical depth to rayonization. This is also nice to understand. So, changing the optical depth to rayonization, if you remember, means changing the visibility function, which had two peaks, the reionization peak and the recombination peak. And these peaks tell us which fraction of the photon that we observe had their last interaction at recombination, and which fraction had their last interaction during rayonization. If photons have their last interaction during rayonization, what happens? It means that more photons rescatter, but when photons rescatter nearby, it means that we lose track of the primordial correlation imprinted on the last scattering surface, because they are rescattered at low redshift in a random direction. So it's like increasing the depth of the cosmic fog that we described on Monday. So if I increase tau rho, I increase my cosmic fog, and so I decrease the correlation between points on the last scattering surface, and I expect that everything goes down, exactly as if I would decrease the amplitude parameter AS. Is this what we observe? We observe it very well for large L, but for small l, the effect of tau does not appear. Why is that so? And that's very interesting. It's because the unique effect of rayonization is not just to blur the last scattering surface. The photons that rescatter close to us during rayonization can still propagate to us, and they will propagate to us from a smaller distance. It's exactly as if we had created a second last scattering sphere. There is a last scattering sphere at a redshift of 1000, and there is a closer and smaller last scattering sphere corresponding to a redshift of 7 when the star forms and the effect of rayonization peaks. And the photons coming from this second scattering surface carry their own fluctuations and correlations. So we should not only decrease the primordial power spectrum, but we should add to the primordial power spectrum a second component, a second spectrum, corresponding to the correlation from the nearby scattering surface. And you can compute the second contribution. I didn't do it in details, but it has a shape like this, meaning that it peaks at very small L. Why at very small L? Well, because this new scattering surface is close to us. So any fluctuation on this scattering surface are seen under a very big angle. So the peak of the second scattering surface is shifted to small l. So we have reduced the main contribution. We add a second contribution, And it turns out that the sum of the two effects is the two effects neutralize each other for small l's. And so we don't see a decrease of the power spectrum for small l's, which is why people usually say reionization induces a step-like suppression of the power spectrum. In fact, it's not really a step-like suppression. It's a global suppression plus the addition of a component that neutralizes the first effect on small scale. But this is more or less a coincidence. And in fact, you can see that it's a coincidence because if you have very good eye, you will see that here the power increases a little bit. Very hard to see, it's very hard to measure also, but it shows that it's really not that you are not suppressing the power spectrum here. You are suppressing it and you are increasing it by nearly the same amount, but not exactly the same. And now we have seen the effect of our 6 parameters, and clearly they are all different. So I did not prove it. To prove it, I would need to run an algorithm that would prove that you cannot obtain one effect from a linear combinations of the others. If you could, there would be a degeneracy between the parameters. But it is well known that this is not the case. The effects are sufficiently different. None of these plots can be obtained from a combination of the other ones. If you read the lecture notes that I have posted online, I have another way to explain it in more details, which consists in looking at the list of the quantities that affect the shape of the CLs. We have already described these quantities. There are 8 of them. There is the angular scale of the peak, the baryon to photon ratio at recombination, the redshift of equality between matter and lambda and radiation, the angular scale of the diffusion damping length, the global amplitude, the global tilt, the late integrated Sachs-Wolf effect, and the effect of reionization, which has this nearly step-like suppression. So there are 8 effects which, from the point of view of a physical discussion, are all different from each other. However, in the minimal cosmological model, these 8 effects are different, but not independent of each other, because they are entirely governed by 6 parameters. If we had 6 parameters introducing 3 effects, of course we would have parameter degeneracies at the end. But if we have at least the same number of effects as parameters, or even more, which is even better, we can clearly say that all effects can be distinguished by the data. And this is why, with just a CMB experiment, you can measure at the same time all the parameters of the standard cosmological model. Now, usually at these points, there is always a student to ask me, and so I ask myself first, okay, this is for the lambda CDM model, but if you look at other models, you will have more parameters. So at some point, you will get some degeneracy. The data will not be able to measure all the parameters. And the answer is yes and no. There are a few annoying parameters which put more freedom into the game without adding new observational effects. And we are going to see one example, and actually I think it's the only example I know. It's the example of the spatial curvature. Tomorrow I will show you what happens when we vary omega k. When we vary omega k, there is no new effect. But we have a kind of safety margin here. We had 8 effects for 6 parameters. When we go to a non-flat universe, we still have 8 effects for 7 parameters. And up to some error bar, we can still measure all the parameters. All the other extensions of the cosmological model that I know add not only new free parameters, but also new physical effects. Tomorrow we will give examples for neutrino mass, for the effective neutrino number, and I think for another one, I forgot which one. And you will see that, yeah, there is more freedom in this case, but there are also more effects, and so you can still measure all the parameters independently. That's why the CMB is really so nice with us. It manages really to encode information about almost all the reasonable physical assumptions that we could make about the cosmological model. And this closes a part on CMB temperature. Yes? question. Very good.
Is there some test to tell if you have some kind of reducible set of parameters?
The question is there a test to know if we are using the right parameters? Yes, of course. When we feed the data, we look at different statistical estimators of the goodness of fit of the model. We compare different models with each other, the minimal model and extended model, using chi-square per degree of freedom, Bayesian evidence factors. We do all these tests, and clearly when you look at CMB data nowadays, this model is sufficient. Then when you add the data on the measurement of H0, it's another story. Yeah. Yes, many questions. So I think you were first, then you, and then you.
How much are you changing the parameter?
Well, this is just for pedagogical purpose, so it doesn't matter. I mean, these scripts are available online, I believe. And yeah, of course, it's a much bigger change than a lot by the data, because the data have typically 1% error bars. So these changes are huge compared to the final error bars from Planck, for instance. Yeah. Yes?
The question is with respect to the omega lambda.
Yeah.
The effect of omega lambda is if you have very low values of L, we are integrating such small effect, right? But as I remember also from your lecture, the variance at low L is very high. So
that's a very good remark. That's a very good remark. We are limited in the accuracy with which we can reconstruct parameters by the noise of our instruments, but also by cosmic variance, which is like a theoretical error that we cannot beat. And cosmic variance is large at small l. So if we have an effect which appears only at small l, we will not have a good measurement of the parameter. And our friend is totally right. This is the case for omega lambda, because omega lambda has two effects. Changing the scale of the peak, yeah, but this is trivial. And this you can obtain by a combination of the others. And then late integrated Sachs-Wolf is only an effect at small l. And so because of cosmic variance, we will never measure this effect very well. And this is why with CMB only, the error bar we get on omega lambda is the biggest relative error bar among the 6 parameters. But there is still an error bar. You cannot do whatever. Just that the data is less sensitive to omega lambda than others. And this is why you want to combine the CMB with supernovae, with BAO, etc. Very good. And there was one here, and then one here. Yeah?
Specific late time effects that make it particularly tricky? Like I know SC only affects like the small scales, but what about lensing? Like which parameters would that?
Lensing. We will see lensing in a few slides. Yeah. For instance, one thing for which the CMB is not good at is complicated model of dark energy with W0, WA. These models are difficult to constrain with CMB only because a bit like omega lambda, they introduce only small modulation of this late integrated Sachs-Wolf effect. So for this, the CMB is not good alone. And yeah, maybe the last one before we move to polarization. Yeah. That's about a general discussion. Okay, we can address this at the end. Now this is not the topic now. Yeah. Okay, tomorrow we will have time for all the final, even during the discussion session. All right, so this is the level at which I wanted to teach you about CMB temperature. And we cannot afford to do the same big effort for polarization. So I will summarize what is the story of CMB polarization in only a few slides. Okay, CMB polarization. Let me remind you that light is polarized in the sense that an individual monochromatic wave has a polarization plane. Very often when we observe light, we have a superposition of many monochromatic waves with different polarization planes. And the question is, do we have in this case a net polarization, or is the distribution of the polarization plane of the individual wave such that there is no net effect? This is an interesting question, can be studied quantitatively. To study this in details, people introduce some so-called Stokes parameter. We're not going to do this. It's enough to understand a few things. The first thing that we should understand is that the photons in the early universe are in thermal equilibrium, strongly interacting, which is why they acquire a blackbody spectrum. But then, because of all this interaction, we said the interaction in a fluid, they always isotropize everything. And they also tend to isotropize the plane of polarization of the photons, such that you are an observer in the tightly coupled baryon-photon fluid in the early universe. You look in a given direction, you will have a sum over all polarization plane for the individual photons, and you will measure 0 overall net polarization. The thermal bath of photons is unpolarized. The question is, the photons that we see today, they are not in thermal equilibrium. They have decoupled from thermal equilibrium at recombination. So could there be that they acquired a net polarization? And to explain this, people very often use simple drawings. Here is my version of this drawing. It's a drawing in a few steps. We're going to think about what happens when we have photon scattering. And for the moment, we imagine that we are still before recombination when there is tight coupling. We have Thomson scattering of many photons arriving from all possible directions close to an electron. These photons are scattered, and we look only at the photons that are scattered in our direction. We are the observer, we are in front of the board, we see these photons coming to us, different incoming direction, but a unique outcoming direction. And so far, I only look at photons that were coming from the top and the bottom. These photons had all possible polarization plane. The net polarization was 0. And to give a very sketchy view of this, we do as if we had half of the photon with the polarization in the plane of the screen, half of them in a direction orthogonal to the plane of the screen, such that it's like a cross, and the average over the two is 0. The same for the photon coming from the bottom. Does Thomson scattering know about polarization plane? Yes. When you look at the details of the Thomson scattering cross-section, there is a term, there is a coefficient that depends on polarization. And it has to be the case because the plane of polarization is represented by a stick with a direction, and this stick is not allowed to change. It would violate fundamental principles of electromagnetism. And the polarization is always defined in a plane, in a transversal plane, orthogonal to the direction of propagation. So suppose that the photons that have here a polarization which is orthogonal to their direction of propagation, but in the plane of the board. And suppose that they arrive there, and they scatter, and they come to us. Their polarization can be transmitted to us while remaining in the same axis and still orthogonal to the direction of propagation. But now we look at the photons which are with the polarization plane orthogonal to the blackboard. It's this stick. If this polarization was transmitted at the end, it would have to be collinear with the wave vector of the wave, and that's not possible. And indeed, there is a suppression factor in the Thomson scattering cross-section that tells us that this photon cannot be scattered in this direction. These are two extreme cases. You could think of all possible directions of the polarization, and you would find that they can be transmitted with a Thomson scattering cross-section that depends on the cosine of an angle, such that the Thomson scattering cross-section is maximal for this case and minimum and 0 for this case. What it means, what it shows is that here I have photons arriving with all possible polarization planes, no net polarization, but these photons will come to me transmitting dominantly one direction of polarization. So I've created a net polarization. Later we will see that this is not relevant, but for the moment it seems that we have created, through Thomson scattering, a net polarization. Now we have the same amount of photons coming from the bottom, and for the same reason, only this polarization direction is transmitted, this one is not transmitted. So it reinforces the effect, and we get a net polarization. Now we are going to look at, yes, yes.
Why the cross polarization is not transmitted?
The best is to use a little pencil. Can you lend me a pencil? Very good. Okay. So we imagine that these photons are coming from the top and the bottom in the plane of the screen, while this is an attempt to show in perspective a photon that is coming through us. So the photon that has a polarization in the plane of the screen does this, boom, and it goes to us. And it works because the direction of the polarization is still orthogonal to the motion and is in the same direction as before. This one is like this. Cannot be transmitted because the polarization would not be orthogonal to the motion. So then the Thomson scattering is suppressed. Je t'en prie. Then we do the same with photons coming from the left and the right. Same story. In this case, this polarization plane can be transmitted, the vertical one, but the horizontal one cannot be transmitted. So for these photons, we are also created a net polarization effect. But now let's consider the two effects globally at the same time, and we make a very strong assumption. We assume that an observer located at the position of these photons would see an isotropic flux of photons, meaning the same number density of photons coming from the top, the bottom, the left, the right, and actually all directions. Is this a reasonable assumption? Yes, it's physically motivated. We say that Thomson scattering, when it's efficient, isotropizes the fluid in the rest frame of the electron. So before recombination, it has to be like this. The electron has to see an isotropic flux of photons from all directions. And then, when I am an observer here, the photon with the horizontal polarization come only from the top and bottom. The one with vertical polarization come only from the left and the right. But when I do an average, I still get zero. I've not created a net polarization. If I integrate over all the directions, of course there are other possible directions, but they are not relevant. I have not created a net polarization. And so it shows that Thomson scattering before recombination preserves the isotropy, preserves the fact that the black body CMB photons are unpolarized. What do we need then to create polarization? Well, we have to get rid of this assumption of isotropy. And we can do it because we know that at some point the photons are going to leave thermal equilibrium around the time of recombination. So around the time of recombination, I am not constrained to assume that I have the same flux from top, bottom, left, right. I could have actually anything. And if I have anything, I can expand this anything in multiples. Dipole, quadrupole, octupole, etc. But what is relevant for our discussion is a quadrupole component of the pattern. Because when I have a quadrupole component, I have two opposite directions with a big flux, two opposite directions with a small flux, angle of pi over 2 between the two. This is a definition of a quadrupole pattern. And in this case, the abundant photon that I have represented schematically with big crosses will transmit a lot of photons with horizontal outgoing polarization. The rare photon will lead to a rare photon with vertical polarization. The two do not compensate each other anymore. I've created a net polarization aligned with the orientation of the incoming quadrupoles. You could do the same for dipole, octopole, any other multipole. It's only for the quadrupole that you get a net effect that does not average out to zero. This is why there is this famous statement that the polarization of the CMB is created by the last few scatterings of the photons around the time of recombination, because this scattering could take place in an environment with a quadrupole anisotropy. So the polarization of the CMB is created at the last moment before they decouple. And how do we expect to observe it? We expect to observe it by the fact that if we look in different directions in the CMB map, and if we use polarization filters, we will reconstruct this net polarization in each point. So we can divide our data, our map in pixels. In each pixel, we compute the average polarization, and we can represent it with a small stick, where the length of the stick tells us how polarized is the light, and the orientation gives us a plane of polarization, of course. So this is a beautiful map of polarization obtained by Planck. And just visualizing this measurement is a nightmare for the observers, because you can visualize it only once you have divided your map into little squares. And then in each square, you define the net polarization. But if your squares are too big, your representation will not be as precise as what you have measured. So you could decrease the size of the square, but if you decrease the size of the square too much, you will see only little points. It will not be helpful. So there is no perfect way to represent the measurement of CMB polarization. But you can do some zooms, and that's a very impressive image here that you can find in the Planck 2018 paper. The guys here have done first a representation of the full sky with a big smoothing size or pixel size. And then to show how much information there is about polarization in Planck data, which is really amazing, they did a zoom over, I should have put a little square, but they do a zoom over a little square here, to show that we have actually much better information than shown here. And then there is a second zoom of a small region, which is here, to show that there is even more information on small scales. The amount of data that we have about the polarization of the CMB is amazing. There is another artistic way to show polarization that I find really beautiful. It was giving the background in my first screen. People have found or developed in Planck, I don't know if it was developed or reused, a very sophisticated image treatment algorithm that brushes these small lines, and these lines follow the polarization planes. And if you zoom, you obtain this kind of Van Gogh picture that are really beautiful. So this is another way to represent the polarization plane of the CMB.
Plane?
Yeah, I should not say plane. I should say it's a stick. It's an axis. Yeah, yeah. Plane is when you think of the wave propagating. Then I don't have your pen anymore. But the wave no, I don't need it. The wave propagates, and the polarization is like this. So in fact, it lives in a plane. But because we see it on the last scattering surface, for us it's a stick. The stick is the intersection of the plane of the wave with the last scattering surface.
I have a question.
Yes.
Those maps are made by Kelvin?
This one I'm not so sure. Yeah, I think they are made by something more advanced. I'm not sure it's in Hillpix. Okay, we go back. Yeah. Yes. Yeah, as usual, when you see a map from WMAP or Planck, a full sky map from a satellite, you have to keep in mind that people are cheating you, in the sense that far from the galactic plane, you have data with very low noise, and in the center, data with very high noise that has been completed with some cheating techniques called inpainting, and that are never used in the final statistical analysis. Yeah. Meaning that some of this information is true, but only some. Yeah. Okay, so we go back to this representation, and what do we do with a map of sticks? We are not going to ask class or com to output little sticks. So we have to find a way to deal mathematically with this situation. What is this map? If it was a map of small vectors, it would be a spin 1 map. A vector is a spin 1 object. But these are sticks. Sticks are unoriented vectors. So they are technically spin-2 objects. So it's a map of a spin-2 field on a sphere. And there is a formalism to describe this. There are spin-2 spherical harmonics. The math are quite horrible, but people know how to deal with it. And when you have a map like this, you can do, actually like for a spin-1 field, a decomposition in gradient field and rotation field. Exactly like in electromagnetism, you would decompose in electric and magnetic field, but this is only an analogy. Here there is no electric and magnetic components, but we still call them E and B for the gradient field and the rotation field. And so I can decompose my map into scalar map. Scalar map means a map that I can represent with a color code like a temperature map. And then I forgot the sticks. I can have decompose this map into a scalar map of E mode and a scalar map of B modes. Who found this? The first, Seljak and Zaldariaga. That was a very beautiful paper in which they explain how you can process this map into E mode and B mode map. I will give the reference in a few slides. Okay, so this information from Planck can be recast in two additional maps. But there is something very interesting going on. The fluctuations we see have patterns imprinted by Bardeen scalars. We said, okay, in this course we study Bardeen scalars. Tomorrow we will spend some time about the role of the Bardeen tensors, so the gravitational waves. But we know that this role is very small, has not been detected so far. So let's pretend that we only have really Bardeen scalars contributing to this map. When you work with Bardeen scalars, you realize that all the fields that you can generate are gradient fields. And so the mathematical structure of these fields is just totally unable to generate a rotation field, and the B modes are expected to vanish. And this is what we observe indeed. So the information contained in the polarization appears first as a spin-2 field, but in reality, after doing this transformation, you reduce it to a scalar map of the E modes only, which can be treated mathematically like the temperature map. So at the end, it's quite simple. This is a way to illustrate what you expect when you decompose a map into E modes and B modes. So when you have a map with only gradient fields, E mode, you expect to see small circular patterns or small star-like patterns. When your map contains only B modes, you expect to see small hurricanes like this, gradient fields. And I show here a famous image that should be interpreted with care, because this image made a lot of noise some years ago. It's some early data from the BICEP experiment, and when it was out for the first time, the BICEP experiment thought that they had detected CMB B modes. And in fact, this is mainly a map of dust, unfortunately. But this doesn't matter. I am only using this map to show you what it is to have E modes or B modes. The spin-2 map observed by BICEP has here already been decomposed into two components. This colors is a scalar map of the E mode. This map is a scalar map of the B modes. And then they put back the sticks derived from the individual maps, such that these sticks are supposed to have only E pattern and these sticks only B patterns. And you see very well the small hurricanes of the B patterns, or the small circles and crosses or stars of the E patterns. Now, when you take a map of CMB polarization, not contaminated too much by dust or other unwanted foregrounds, you find that the B signal is compatible with 0 and the E signal is instead very well measured. Okay, so you can do all the theory that we have done for the temperature at the level of polarization. What did we say? We said that for polarization, the magic quantity is a temperature spectrum, which is a correlator of the ALMs of the multiples of the temperature map obtained by this integral. Now I add an index T for temperature on my photon transfer function. And we have seen that this photon transfer function is given by the line of sight integral of Zaldariaga and Harari. So what Seljak and Zaldariaga have shown a few years later, 96, and there was also some independent work, very beautiful also, very interesting by Wayne Yu and Martin White, is that you can do the same for your E mode. Once you have your E mode map, you can decompose it in multiples, you compute the correlators, it gives you a CLEE, which is given by an integral in which you exchange the temperature transfer function for a polarization transfer function, also given by a line of sight integral. I should have here a small index t and here a small index e. And again, this line of sight integral is expected to describe the physical effects contributing to polarization. Do we expect Sachs-Wolf, integrated Sachs-Wolf Doppler? No, no. We explained that polarization comes only from the fact that the last scattering of the photon takes place with maybe a quadrupolar environment. So we throw all this away, we keep the structure, we keep the visibility function because the effect comes from the last scattering surface, we keep the Bessel function for the projection from wave number to multiple space, but the function which is here happens to be θ2 plus very small correction terms that I don't detail and that you can find in the specialized literature. So the formalism is the same, but instead of being dominated by the intrinsic temperature which comes from the monopole θ0, you are dominated by the quadrupole of the photon anisotropies on the last scattering surface. And you can compute this, you can do the same reasoning that we did yesterday and today. In particular, I have also a color plot for this. This was our color plot for θ0 as a function of time and scales. It was very useful to understand how the modes vary inside the Hubble radius and until recombination. But I can do the same plot for the quadrupole θ2. The quadrupole θ2 remains completely negligible until recombination. Why? Because until recombination, I have this tight coupling fluid in which everything is isotropized, and we said all the θL with L bigger than 2 remain 0. So I have only gray color here, which means 0. But when we cross the Hubble radius, θ2 becomes non-zero. And so this θ2 will act as a source for the CMB polarization spectrum. And this source comes from two regions here. The main region is recombination. Why? Because of the source function, we have the visibility function. The visibility function is very peaked at recombination because this is where most of the photons that we see have had their last interaction. So we should look at θ2 at recombination, and we see that θ2 was negligible on super Hubble scales, but had some patterns here with oscillations which come from the acoustic oscillations. Actually, θ2 is almost a second derivative of θ0. So we have some patterns here, and they will contribute to the polarization spectrum at the end. But there is a correction to this. Sorry. The G has another small peak at rayonization, and as we said, it means that there is like a smaller scattering sphere close to us. This smaller scattering sphere corresponds to a redshift of 7, which on this map is around here. And at this redshift, I also have a bit of colors for modes that are close to the Hubble radius. So I will have also a contribution from the quadrupole here to the spectrum, meaning that when the photon rescatter at rayonization, they also rescattered in an environment with a quadrupole. So some polarization will also be generated here. And when you look at the shape of the power spectrum, look only at the black curve for the moment. You get this shape. Here I have the logarithm of LL plus 1 CLEE. The LL plus 1 is for the same reason as before. We always rescale our CL by LL plus 1 in order to have something that would be flat if the transfer function was flat. Yeah, we are coming to a very good point. Thank you. Okay, and I have first this shape. This shape comes from the pattern at recombination here. The quadrupole is maximum around the scale crossing the Hubble radius at recombination. And when I go from the transfer function to the spectrum, I have this overall peak modulated by acoustic oscillations. The reionization produces the same shape, but smaller, because only a few photons rescattered, and shifted to smaller Ls, larger angular scales, because this new scattering surface is closer to us. So everything is seen under a bigger angle. And the sum of the recombination part and reionization part gives this CLEE spectrum. And how do we know that this is really coming from reionization? Well, we can recompute our spectrum increasing tau rho. The path from recombination is then slightly erased, because for photons coming from recombination, reionization is a blurring, is a fog. The part coming from reionization is enhanced, because I'm changing the position of the last scattering surface of reionization. So what is interesting here is that the shape we get here is directly measuring the optical depth to reionization, and this is the best way we have to measure it. So if we know the value of tau rho, it's because we have measured this peak called the reionization peak, with still an error bar coming from cosmic variance, but it's still quite well measured. And I think that this closes CMB polarization, so we stop here. Very good. So before the questions, I tell you just what we do tomorrow. We spend 1 minute on CMB lensing, then we describe the data, the measurement of the parameters of the lambda CDM, the measurements of parameters beyond lambda CDM, and we close with a discussion of the role of tensor, gravitational wave, and what the CMB tells us about inflation. And finally, there is a slide about future observations. Very good. Are there some questions? Everybody is exhausted. Yes, me too, by the way. Yeah. Yeah.
About how can you know that there is no correlation and no degeneracy between the parameters?
The question is, how do we actually know that there are no degeneracies between parameters here? The method. You can do it in various ways, but the simplest way is to do what everybody is doing, which is fit the data with an algorithm like Monty Python, like Cosmo MC, like Cobaya, in which all parameters are fluctuated simultaneously. And if there is a degeneracy, then in your parameter space, you will have an endless direction along which you can fit the data. And it's not the case. Especially with this minimal model, you get beautiful tight ellipses. And you know that all the parameters are constrained.
We can modify the cohomological parameters, and we can compute the power spectrum, the correlation function.
Yeah, but the point of our friend is that I can show these plots and do some blah blah and tell you the effects are all different, but you will be convinced only when you have the proof that I could not take a combination of these ones, for instance, to reproduce this one. And this is implicitly what is done when you do a global fit to the data with an MC-MC algorithm. Yes?
After BICEP 2, were there new releases?
So BICEP 2, I will show tomorrow. BICEP 2 kept improving their results, but there is still no detection of primordial B modes. We will spend, 20 minutes on this tomorrow. It's an important topic.
The Cubic Observatory in Salta is looking for remote. Cubic Observatory.
Cubic, it's one of the ongoing experiments. Yeah, Cubic, absolutely. Yeah. Sorry? No, because it would be totally unrealistic to assume that the same mechanism would have an influence on the CMB and on nanograph. You could do it with very extravagant models, but in principle, what can contribute to the CMB are gravitational waves from inflation, and you need to torture your model in order to have an impact on nanograph. And I think there is even a fundamental argument saying that this is just impossible. I forgot, but it's not unlikely, it's impossible. I will try to remember the argument for tomorrow. Sorry?
Too much dark radiation.
Yeah, exactly. If what you see in the nanograph data were gravitational wave from inflation, the total energy contained in this gravitational wave would be so big that it would contribute to the effective neutrino number, because the density of gravitational waves scales like radiation. And it would increase N effective above the limit allowed by the CMB. So we are sure that what nanograph sees are not beam mode from inflation that would be visible at the same time in the CMB. Has to be something else. Yeah. Thank you.